you? How are you today? Sorry.
Good.
Okay. So we talked about making change before, yeah? And today is another problem of making change. Let's say we have
Making change
One.
equal.
1p,
1p.
2p, 5p,
1.
20p, let's say. Okay. Okay, and then 25, if there's 25, okay? Just make it up.
25. That's anyway.
Okay, maybe 25 to 1, 10, 20, 25. And then I want to make 60p. Okay?
How many?
How many minimum number coins?
Okay, so we want to find the minimum. So we work it out as starting from the biggest because
Okay, so one question is that this is the target we want to make the change, and then you can suppose you have as many unlimited number of each coin, so you can have unlimited of 1p, 10p, 20.
3. The minimum is 3.
Why? So can you tell me?
Because we can have 25, 25, 10, 20, 20, 20.
Yeah, well done. Okay, so this is unlimited. It's like unbounded. Yeah, unlimited. For each one, you have a list of the.
Definitely will take ages for one.
One. Yeah, it'll be 60. Yeah, it will be 60 coins.
61.
So this is the one example of unbounded knapsack. You know, knapsack, unbounded. What's unbounded mean?
Unlimited.
Unlimited, unbounded. Yeah, there's no bound. Yeah, knapsack. What's knapsack? A bag.
It's a bag. Yeah.
Knapsack problem. Okay, so.
A big bag.
So we can describe this problem in a very general way. Is that we are given a bag. Yeah, we are given a bag of capacity 60, right? A knapsack 60, and we have a list of the different items, right? Eric?
Mm-hmm.
Items, and each item has different weight, right? And we want to minimize the number of items to put in the bag, right? So you can put 20, 20, 20, or you can put 25, 25, 10. And in both cases, it's the same. You need to tell me it's 3, number 3. Got it?
Yeah.
Okay, so how can we do this?
Okay, so we start from we sort it first, then we start from the biggest.
Okay, so you sort it first, from the greedy, yeah? And then what?
And then we do it again and to see
how many you can get, right?
Yeah. So it's 50, and if you do it again, it will be 75. So you can't get any further.
Okay, but this may not work, right? Why is that? If I don't have 10, then your greedy is not working, right? You put the 25. You start from the try to pick the most heaviest, right?
Yeah.
But then you run out of choice, right?
Yeah.
Yeah. So the greedy may not work, am I right?
If the target equals 25, and you only have like 1,
Okay.
20,
Okay.
and like
5, yeah. 4.
6.
Okay. Then you need 6. Yeah, because 20. Oh, maybe no. You can have 4, 6, and 1. Yeah. So that would be 5, and then you can have 20 and another 5 ones.
How about 3,
okay.
7, 10, and the
I
target
see.
8?
Okay. Eric, coming back to the question, yeah, you pick the most heaviest. You try 25, but you're running out of, you don't have 10, and then you can only make it up with 1, right?
Yeah.
So that may not be optimal.
So,
The greedy is not working here in this case. I'm just trying to prove that your solution may not work. Yeah, I can always find some input that breaks your algorithm. Okay. Yeah. Okay. So how can we do this? We can brute force. We can search. Yeah.
Yeah.
We can always search, but
Are you not using a rubber?
that's okay.
Because we say so.
Yeah. Look. That's coins. Yeah. We have coins and we have a target. Right. A target. The maximum
It
capacity.
doesn't have to be.
So we can search.
Doesn't have to be P.
P. Yeah. No. Look.
DP.
Look 20. Look this one. So for each one, we can start from the current. We can pick these, or we can pick the next one, right? Yeah. We can for each item we can pick current, or we can pick next one. So it's a search. Yeah. Yeah. So this is going through the depth search. Yeah. Yeah. Yeah, that will work. Okay. So how about if I tell you you can solve this problem by dynamic programming? Do you still remember dynamic programming? What's dynamic programming? What's dynamic programming?
Remember memorization. Memorization, top down, bottom up.
Yeah, remembering. So the key point here is remembering, yeah, memorization. Yeah? So if I tell you that f function, fa is the number of the coins we need to make up change a, right? Yeah. So what does it equal? I have a list of items of coins here. I have a list of coins here. Let's say the coins. I have coins, which is a list, yeah. And I can say D belongs to coins. Yeah, this is belongs to. So does it mean that I can always pick the minimum? Look, Eric. Eric, look, pick the minimum. Eric, what does it equal? FA equals mean of what? Of A minus D plus 1, right? For D in this. Yeah? Eric?
Yeah.
What does it mean?
Jump!
Look, Eric. Eric,
Yeah.
what's that? 1, 5, 20, 25. And we want to put a 60, right? We want to come up with 60. And what does it equal? F60, what does it equal? Equals mean of what? Of F60 minus 25, F60 minus 20, F60 minus 5, and F60 what?
Minus 1.
1. And all of these plus 1, yeah? Because
it wasn't the 5 last time.
Yeah. I'm just making up, okay? So what does it mean? Look, if I want to make up 60, right? I know I can make up 25, right? If this is the coins of making up 6 minus 25, and why is plus 1? Because I need one more coin, right? Yeah? Am I right? Can you explain to me what's this? F60 minus 20 plus 1. What does it mean?
Okay, so so 60 minus 20, and 20 is a coin.
Yeah.
Yeah, and 60 is a target we want to get.
Yeah.
And we add 1 because we need a coin.
Okay, so what is F60? I know the difference between F60 and F40 is 1, right? There's a 20 coin, yeah? I know there's 20 here. Yeah. Alright? Alright? Suppose we already know F40 here. Yeah? Then we can use this value. Because this value we already save it. Yeah? So we don't need to compute this again. We know F60. Because F60 equals F40 plus a 20 pound coin. 20 coin, right? Yeah? And then this, look, F40, what's F40? F40 equals F mean of F40 minus 25 plus 1. F40 minus 22 plus 1. F15 plus 1. And F19 plus 1, yeah? Yeah? You see? So in this case, I updated all the values between 1, 0 to A. Right? Right? I don't need to calculate again. Does it make sense? Yeah? And if dynamic programming, we can always use implement in what? In which?
No, but
How many
top
ways?
down.
Top down and bottom up, right?
yeah, 2.
Let's implement the bottom up first. Can we do it? Look, Eric. Define F, and then that's the amount, right? Amount and the coins, yeah, coins.
Column.
Okay. Look, Eric. So first of all, we need to what? Have this array, a list to store the F, right? F0 is what? F0. If the 0 nothing, how many ways can you make it? Nothing. It's nothing. Yeah. So look, let's say, let's change this to dp. Okay, and then F equal Look, Eric, 0. This is F0, yeah? Plus, at the beginning, look, Eric. So at the beginning, we maybe it's not possible to make up the money, right? If you want to make up 60 and then you only have you only have 13, there's no way to make up 60 using 13, right? Yes? All right?
Yeah.
Does it make sense? So if f, let's say if look, for example, f60 equals f14, 16 minus 60 minus 14 plus 1, yeah? Alright? But if this one, we cannot make it. Let's say we make it a very big number, right? Infinity, right? If this is infinity, right?
That would be possible.
Because there's no way to make up f60 minus 14, yeah? For 13. So that initial value is mass.infinity times amount, right?
Hey, why is like that?
Wow. This is, look, so f is the list. The first list is 0, and then they are a or a times of the mass dot infinity. So what's f? F it will be like this, Eric. Look at this. Look at here. So what's f value? It will be 0. The second value will be what?
1.
No, mass dot infinity. So it will be infinity, and then infinity, and then how many of these? How many of these? This is the list. F will be this.
The list minus 1.
No, a. Come on, times a here. This is, look. That's what it means. The first one 0 plus a times of this. Okay. So that's the list of f. F equals that. Yeah. Okay. And then what's next? And what's next? And look, for what? For I in range.
What's I?
A variable, yeah. For I in range, start from what? From 1 to amount plus 1, yeah. We want to calculate the fi value, right? And then for coins, C in coins, yeah. We have coins, alright? Look, see. Yeah. Look. If the current amount is bigger or equal than C, right? Alright. Yeah. If the amount is smaller than the coin, it means it's not possible, yeah. If it has to be bigger, yeah.
Yeah.
And
At least one of them.
and what? And F what? I minus C, right? What did I say? Fi minus C not equals mass dot infinity, yeah? If we can make up this, yeah? So what should we do? Fi, we are calculating the Fi value, yeah? Equals mean Fi minus C plus 1 and Fi, right? We want to keep the minimum. Alright, Eric?
Yeah.
Does it make sense, Eric? Okay? Brian, are you okay? Eric, explain it again, okay? Fi is the value we want to calculate, the amount, right?
And
We start from the y. This is bottom up or top bottom?
Bottom up.
Why is bottom up? Can you give me a?
Because we are calculating from bottom to the top.
Which 4 is from the bottom to the top? There are 2 4. Pick one. Which one is from the bottom to the top?
This one?
Yeah, because Fi start from what? 1, right?
Yeah.
F0 is 0. We already know. F1 to A. So the I will start from 1, 2, 3 until A, right? Yeah? For each 4, and I choose the coins. And then if I bigger than C, and I might, what's this, Eric? What's this?
Not equal.
I know, what does it mean here? What does it mean here? I just told you, I explained 2 times.
If the F. So F the value minus the coin
Yeah.
is not
Equals to mass dot infinity. That's the initial. What does it mean?
I mean, it can be, you know.
You can be. We know already how to make up the money, right?
Yeah.
For example, 60, and we already know how to make up 40. If there's no way to make up 40, and we don't need to calculate this, right? All right? Yeah.
Yeah.
Okay, and then what should we return? The last value. Return which one? Return what? F.
I.
What?
Return F.
F what value? What are we calculating here?
A.
A. Or F minus 1, yeah? The last value, yeah? Alright? Yes? Okay, look, if F minus 1 is a mass infinity, it means there's no way to calculate it, right? Yes? Alright?
Yeah.
Yeah, it could be possible that we can't make anything up to that F amount, right? Like 60. If you only have 13, about 13 pence, you can't make 60 using the 13 pence, right? Yeah? Does it make sense? Because 60 cannot be divided by 13, right? You can only use 1, 2, 3, 4, and you can't make up 60, alright? Alright, does it make sense?
Nothing far.
Now I'm still going to talk about top down. Remember, what's top down?
New memorization. We start from the top to the bottom, and we normally have.
What's the time complexity for that one? I forgot to ask. If the amount is A and if there are n numbers of coins, what's the time complexity?
OAN.
OAN, yeah. Why is that? Because we have a for loop. For the first for loop, we have that's amount, yeah. And for the second for, when the coins, what's the time complexity of the second loop? For the coins.
N.
Yes, and then times together you'll be OAN, right? What's the space complexity? Remember this, the f function. What's the space complexity?
Why you're drawing F?
No, remember the space complexity for the bottom-up dynamic programming. What space are we using? The f function. F function is what? We are calculating f0, f1, f2 to fa. So how many of these?
FA.
Oh, LA. Okay, that's space complexity because we just need a list of f function, yeah? Yeah? To A, right? Okay? Okay, now bottom up. Top down, sorry. Top down. Top down. Define,
Cash.
let's say
Cash.
F.
Cash.
Okay, we put a cash here.
Knew it.
Cash and A. Okay, let's say A. If A equals 0, what? We need to define a base condition, which is if A equals 0, return what?
If return 1. Wait, return 0.
Yeah, remember that thing, dp equals 0 plus times infinity, right? Yeah, A times infinity, remember the previous one, but basically it's the same. It's the same implementation, same idea, but different implementation, yeah? Okay? Now what? I have this A. I want to calculate the A, and I have, let's say, answer equals mass dot infinity, yeah? Alright? At the beginning, I'm not sure which one is it. Ryan? Listen up, yeah? Yeah? And then I need to iterate over the coins, yeah? Okay? And look, it's the same. If, what? Okay, look. If coin is smaller than equal what? If the coin is smaller than equal what?
It's smaller than and equal
If the coin,
to A.
yeah, if the coin is smaller than A, right? Then we can check. And let's say x equals f A minus what?
A minus.
Now the coins is smaller than the A, and I want to try.
A minus C.
Yes. And if x is not equals mass dot infinity, yeah? If we can make it, yeah? Alright? And answer equals what? Can you tell me? Answer equal what? And return. Oh yeah, return.
I answer.
Yeah, that's very obvious, yeah? And
And you'll do that one.
No, this is the key point. What's key? What's this?
Answer equals minimum.
Yeah, minimum. Yeah, you know what I'm talking about. Because we want to calculate the minimum of what? The minimum. What?
Answer.
Answer, yes. We want to keep updating the minimum. And then what? And what?
A.
What? A? A is the constant. We don't.
C.
What are we calculating? X, yes. There's one mistake. There's one problem. You're so close to it.
Mass infinity.
There's a. No.
Mass infinity.
X is FA minus C. If we use the coin C, then how many? FA, what's the FA and F minus A minus C?
What?
What's the difference between FA and FA minus C?
C. Minus C.
60p, and we have 40p. We have 20p. So how many coins difference? The 60p and 40p.
20p.
20p is how many coins over this? How many coins? The number of coins. No.
What?
I have a 60p. 60p is the target. And I have a point 20p. Yeah? And now we want to know the number of the coins, the minimum number of coins to make up 60. Yeah? So F60 equals F60 minus 20 plus what? How many coins?
Plus 1.
Yes! And what's here?
Plus 1.
Yeah, x plus 1. Does it make sense? Because we already have coin C. We know, we calculate FA minus C. We use the coin C. So we need to add it back. Plus 1. Alright? Yeah? What's the time complexity for this one as well? What's the time complexity?
N.
This is N and that's A. What's the time complexity?
A-N.
Oh yeah, it's the same, yeah? What's the space complexity?
A.
Yeah, oh A.
Yeah.
But this one is recursion, yeah, with the minimization. But if this A is a minion, what does it mean? It needs to call this function many times, which is not good, right? So it's better to, in this case, the bottom up is preferred. We prefer the bottom up, right? Because we don't call the function over and over again, right? Because there's overhead. There's overhead to call this function, right? The computer needs to call a function, am I right? Yeah? So in general, the advantage of top-down, right? Advantage of top-down is that it's very, human readable, am I right? Because look, I just defined if A equals 0, do this. Otherwise, do this. Calling this recursion is human readable. You friendly. But bottom up is more like computer friendly because the computer don't need to. You tell the computer more efficient way to save up the values. Am I right? Yes.
Yeah.
They're both equivalent, but they're both in terms of the algorithm, time complexity. In theory, they are equivalent, but in practice, we prefer the bottom up, right? All right? Okay, and
Not so far. Not so far.
Okay.
No, so far.
yeah. Well, we have used the coin. We have tried the coin.
Fix this,
Yeah.
and you'll do that bit.
Come on.
X equals something about C.
Yeah. Look, we are currently. We want to Eric. We are currently making up the A, and then we want to try the C value. So what? F we we want to call a value. F what? F what? F
A.
what?
A.
F what?
F.
Yeah, calling the recursion, right? This recursion, you say recursion and what? Currently A, if coin is smaller than A, so what do we need to do? If this is A, this is C. Come on, it's right in here.
5.
Yeah?
A minus C.
Yes. Come on, do you understand? Yeah?
A minus C.
Yeah.
Booyah.
We're calling it, yeah? And we plus one here, right? This is the dynamic programming, okay? We talked about this
I'm
before.
the one.
Okay, that's it for today.
Hello, bye bye.